In today's video, we're going to discuss what confidence intervals are, but perhaps more importantly, we're going to discuss how to interpret them. If you're new here, my name is Olivier and I'm a certified math and physics teacher in Ontario who is currently doing a master's in statistics at Carleton University. Alright, so we're just going to dive into it. What you see on the screen here is you have a bell curve. Let's just get rid of the dots. That's a normal distribution. And on the x-axis, the horizontal, those are IQ scores, for example. So IQ score is a measure of intelligence, good or not, whatever. And the average IQ score, I think it's by definition, not sure, tends to be 100. So that's why you see this line here at 100. That's 100 on the horizontal. And you see that there's the highest value of the bell curve. So that means that there's the highest probability of getting values near the middle, right? Near the average. And it tends to be normally distributed. So that means that the probability of getting an IQ of 95 in that range is about the same as getting an IQ of 105. It's symmetric around the mean. And the further away you go from the mean, the less likely. So that's why the tails are slim, right? So for example, there's not that many people that have an IQ between 125 and 130, and it's symmetric, so that would be between 70 and 75. There's a lot less people that have this kind of IQ than between 90 and 95, for example. And you can measure the area under the curve to figure out the probabilities, but that's getting beside the point. Okay, so now that we have this idea, we can basically measure the IQ of random people. So the first thing we're gonna do here is if I click on the sample, I've measured 5 different people. So the points here, this person had an IQ of 96. That's why they're on the left of the vertical line. They're below 100. This person in the blue study had an IQ of 83, and the green study 98, 95, and 101. So this 83 here is actually pretty far from average, but this is why it's called a random variable. On average, most of them are going to be close to 100, but there is some variation. It's a random variable and it should roughly resemble the bell curve. The height of these points, it's just to separate them, you'll see, so don't worry about it. So then if we measure another one, so now we have 10 people in total, 2 in each study. So the red study here, you have a 96 and 107. So let's say you measured 2 IQs and you wanted to what you could do is try to figure out their average, right? And compare that to the true population average of 100. So for example, if you have the averages, this is the dashed line between them. It's basically the middle of the 2 points. So here, for example, you have 98 and 94. The average is going to be somewhere close to 96, and it is, right? So this is the average, and then what you see, the band is the 95% confidence interval. So that's the main topic of the video, so that's what we're going to explore. But look at these 2 points. The first point was 83, and then the other point is also 83. It's probably there's some little decimal that's different, but getting 83 once is unlikely, and then getting another 83 is unlikely, but it happens. Like through random simulation, that's gonna happen. And if you measure people's IQ, you might get 2 people with an 83 score, and then you're gonna get a very narrow confidence interval. So a lot of people would misinterpret this and say, oh, there's not a lot of variation, and that means it's a very accurate confidence interval. We can be 95% confident that the true population average is between like 82 and 84, for example. But that would be a misinterpretation of the confidence interval, and that's why it's super dangerous, because if you look at all the other confidence intervals, they all include the population mean of 100, but they're pretty wide. So the way to get around this issue is to generate more observations. So now let's go to 3 observation. And just with one more patient in each study, you see how you have 2 points here and then 1 point here. The blue study now is super wide and it catches the population mean at 100, right? So just one more patient in your study makes a huge difference in interpretation. So that's the danger of having small samples. So then if we go to maybe 5 patients in each study, now you have that all the confidence intervals have the population mean, but still the green study, they're all relatively close to the mean, and you could interpret it as, oh, it's a better confidence interval, it's more representative of the mean, we can be more confident that that's the right one. But not necessarily, right? They're all coming from the same distribution, and that's the beauty of this simulation. So now if we go to 10, you see that the intervals are all getting narrower. That's because the standard error shrinks as the number of observations increase. So that's with 10. Now look what happens when we put 20. They still all get closer and closer to the population average, and they shrink in width. But this one is starting to get away from it, right? So just through bad luck or randomness, you're getting a lot of people and a participant in your study that are above average, that have IQs that are higher than 100. So if we increase the number of points here, your confidence interval is not going to catch the population average. So if we go to 30, and turns out when you add 10 more participants, you're actually not catching the population average of 100. This is 100, and your confidence interval is probably like 0.007. So here you would conclude through your hypothesis test. Let's say that you put the null hypothesis to be 100. With this particular study, if you measured these 30 red people here, you'd conclude that we can be 95% confident that the true population mean is between those two values, right? And that it differs from 100. We can reject the null hypothesis. But here in this example, that would be an example of a type 1 error, because we're rejecting the null hypothesis although it is true. And there's only 5% chance of that happening, but it did happen in this red study. The 4 other one would have made the right conclusion, but mistakes happen through randomness, and we need to be aware of that. Okay, so now let's move on into the second part of the video where we explain 2 different interpretations for the confidence intervals. So this red interval here goes from about 100 to 107, 108-ish. Would mean that if your null hypothesis is between 100 and 108, you would not reject the null hypothesis. So but in this case, our H naught or null hypothesis would be 100. So we do reject it. If you recall, it is outside the interval. But for all the other ones, if you have null hypotheses inside of here, in this range, so 95 to 104, whatever it is, then you would not reject it, and you couldn't reject H naught that it is 100. So that's an important thing to realize from this is if we fail to reject the null hypothesis, it doesn't mean that we can accept the null hypothesis as true, because there's varying null hypotheses that could be true, right? This for the blue sample here, if you had a null hypothesis of 95, then you would accept it as true, but no, we know that the true thing is 100, right? So and it could be 96, it could be 97, and all the way up to 104-ish. So it's not like you can accept the null hypothesis as true, you just fail to reject it. So that's takeaway number 1. So now for the other interpretation of confidence intervals, I'll head over to this simulation, and it's done by Christopher. I think they're a Swedish statistician, psychiatrist, and researcher, and I'll put all the links in the description below. But basically you have a similar situation here. We have a sample size of 5. So if we go back to Desmos, that's when n was 5 here. And every time there's a line so there's 5 points in each study. And every time there's a line here, that's a new study, okay? And instead of being 100, it's 0, but that's the same thing. And you see that it's hovering. And then once in a while, you're going to get a line that misses the confidence interval. So like these red lines here, this one here, it didn't catch the population average of 0. So but most of them are going to catch the population average of 0.
And what percentage, which proportion of them are going to catch the true population mean of 0? Well, it's about 95%, depending on your alpha, right? So here alpha is set to 95, but you can play around with it. But your coverage probability, and this is what it's saying, this is the coverage probability, it's going to be around 95% in the long run. But any individual line, we can't say that we're 95% confident about that one. So I'll just read the paragraph about the visualization because I think it's very good. Some say that a shift from hypothesis testing to confidence interval and estimation will lead to fewer statistical misinterpretation. Personally, I'm not sure about that, but I agree with the sentiment that we should stop reducing statistical analyses to binary decision making. The problem with confidence intervals is that they are as unintuitive and as misunderstood as p-values and null hypothesis significance testing. Moreover, confidence intervals are often used to perform hypothesis tests and are therefore prone to the same misuses as p-values. So that's just a word of caution, but there's 3 points that we should consider. 95% confidence is a confidence that in the long run, 95% of the confidence intervals will include the population mean. It is a confidence in the algorithm and not a statement about a single confidence interval. So this is exactly what it's saying. So if we did a bunch of studies, 95% of the studies would catch the true population mean. But each line, we can't say that we're 95% sure it's there. So in frequentist terms, the confidence interval either contains the population means or it does not. It's either that it catches the red dashed line or it doesn't, right? You can't say that we can be 95% confident that this particular one has it. The last point is that there is no relationship between a sample variance and its mean. Therefore, we cannot infer that a single narrow confidence interval is more accurate. In this context, accuracies refer to the long-term coverage of the population mean. Look at the visualization above and note how much the width of the confidence intervals can vary. They can still be narrow but far away from the true mean. So to explain this point, we need to go back to the Desmos. When we had 2 observations here, and that could happen with 5 or 10 observations, is this interval is the most narrow one. But it's very far from the population mean. So accuracy does not have to do anything with width of the confidence interval. All it's saying that you have a narrow confidence interval is that you didn't have much variation in this particular study, but maybe all the people that you measured IQ were all homogeneous, right? They were all close to the same by random chance. Or if you sample a particular course in university, for example, well, it's more likely that you're going to have people closer in IQ than if you measure random people on the street, for example. So that was it. I hope you've enjoyed this video. I hope you realize that confidence intervals might not be as intuitive or as easy as they sound. So just be careful when people cite the science and, oh, we're 95% sure, 99% sure, and all of that. It's really dangerous to think that way. And even me, who's did statistics for almost 10 years now, on and off, I'm still going to update my belief. This video is probably not 100% right in my interpretation. It's just where I'm at now. So keep learning and keep questioning. That's basically the same thing. You can't trust the numbers blindly. That's a big takeaway in general from statistics. Make sure to like the video, subscribe if you enjoy this, and check out the videos appearing on your screen. The best way to support the channel is to share this video with your friends. Thank you for watching, and as always, I'll see you next time with Do the Work.